Hey folks, we're back. We're talking about impulse this time. Last time I talked about momentum. We defined momentum. We gave it a vector quantity called p. Vector variable, I suppose, is a better way of saying it. We said p was going to be the variable of momentum. We said that p was equal to mv. And we showed that we could get force, we could get acceleration and all that jazz from momentum pretty easily just by taking a derivative. But if I take an integral of the force over some time, I'm going to get this change in momentum. So that's where I want to pick up. And I'm only going to look in a specific direction for right now. Of course, momentum is a vector. I need to have consideration of all directions when I think about this vector right now. But for right now, I really just want to think about it in one direction, and we can generalize from that. So delta px in the x direction is going to be equal to the integral of t1, t2 of fx of t dt. All right, so we're thinking about a force in the direction of the x direction, but variable in t as a function of t, and then multiplying it by dt as we integrate. So we're going to say this this left-hand side is our change in momentum, but we're also going to make that equal to this right-hand side here, which we're going to call the impulse. Right? The impulse in a system is technically, the integral of f of t dt from t1 to t2. But we're also going to say that that's the change in momentum of that time as well. So it's like a little triangle here. We have impulse, which we are going to give the variable j. Again, why j? I don't know. But impulse is going to be an uppercase j. It is still a vector. It's still a vector. But j is equal to this integral of f of t dt. But it's also equal to delta p, right? So they're all equal to one another here. When we think about, let's just draw a really rudimentary plot here, some time, and then some force in the x direction. Let's give it newtons here. I'm going to have some impulse, right? Some amount of force over a given amount of time, right? Actually, let me just draw this a little bit better here. That's a little bit nicer. I want to make sure that it's 0 before we start. After we start and before we end a little bit here, just to prove a point, right? So now we have T1 and T2. Definitively, these are where my force begins and ends. So what we're saying then is that the integral underneath this curve, right, the area underneath the curve, is equal to our impulse. All right, that's what we can say is that the area is equal to j, our impulse. I can also talk about j as maybe the average f over this time period, right? So what we can say is that j equals f average times the delta t, right? The time period over which f is applied. That is a perfectly fine way of doing that as well. This is a little bit more convenient of a way of calculating our impulse sometimes, or just talking about an average force simply because it doesn't require any integrals, right? It's just an average force, so I can just multiply f average times delta t. This, I really do want to make this parallel here. This looks a lot like energy, right? Just kind of vectorized in a certain way. If I think about this, delta, I'm still working in blue, oh well. Delta K is equal to the work done externally. That's what we were saying in in Chapter 9 when we thought of everything as a work. We weren't thinking about potential energies yet. So everything did work, and so any work done on my system changed its kinetic energy. And we defined that as the integral from x1 to x2 of f dot dx. Right? Now what we're saying is delta p, our momentum, our change in momentum, is equal to some impulse, right, which is the integral from t1 to t2 of f of t dt. Right? So there are a lot of parallels, not only just with the structure here, but in how we're going to talk about our systems being isolated, non-isolated, interacting with environments. We're going to see a lot of parallels between work and impulse. So that's where I want to leave it for now. This is, again, just laying the groundwork to clue us in that we are going to approach momentum problems very similar to how we approached energy problems. So just kind of have that in the back of your head as we move forward. Next time I want to talk about the conservation of momentum. We're going to add a new conservation law to our plethora of conservation laws, it seems. We'll go through the derivation a little bit pretty lightly. The big thing to remember is that it's always conserved, and if I'm not seeing a conservation in my system's not big enough. All right, so that's a teaser for next time. I'll see you back here, and yeah, have a nice day.